In Chapter 3, which we're starting today, we're going to use calculus to analyze graphs of functions. So in Section 3.1, we're going to talk about extrema on an interval. Extrema are extreme values, like highest and lowest values. We call them maximums and minimums, and you can see from this graph what we're going to be looking for. Obviously, since we have graphing calculators, we can identify them without using calculus, but we still have to analyze them, the graphs, algebraically with calculus. So we're going to be looking for maximum values, minimum values on an interval. And I forgot to bring home my notebook tablet, so I'm going to be having to use my mouse, so I'm sorry about that. Absolute extrema. Here's some vocabulary for you. The maximum or minimum value of the whole function, or on a specific closed interval. And remember that absolute extrema is always in a closed interval, and it could be at the end point of a closed interval. All right, new vocabulary again. Closed interval means that the endpoints are included. So an absolute extrema can only occur at the endpoints of an interval, or it could be the middle, some highest or lowest point in the middle of the interval. Endpoint extrema are those maximum or minimum points that occur at the endpoints of an interval. So look at this function, f of x equals negative times the quantity x minus 2 squared plus 5. What would be the maximum value on negative infinity to infinity? So this interval is not closed. It's on the whole graph. So this maximum value, since we can tell this graph goes down forever on both sides, but it has this maximum value up here, just by looking at the graph, we can tell that the maximum is 5. Maximums are y values. But if I ask you where the maximum occurs, then you would say x equals 2, or at 2, 5. But if I ask you what the maximum is, you have to give me the y value. All right, what if I want the minimum between 3 and 5, and these brackets mean we're including 3 and 5? Sorry about that. So here's 3. Here's the x value of 3. We're including that point. And here's the x value of 5. We're including that point. So just looking at this piece of the graph, what's the maximum? You can see that the maximum, whoops, minimum, well, I don't know why I said maximum. Minimum value is negative 4. It's this value right here, the lowest value, negative 4. Okay? That's on the closed interval, so we do include the endpoints. How about the closed interval from 1 to 3, including the endpoints? So here's 1, and here's 3. I gotta get a pen again. Sorry about this. The interval from 1 to 3, here's 1, and here's 3. In between there, these two are minimum values, but I'm looking for the max. So the maximum value is the y value of 5. If I asked you for the minimum on the interval from 1 to 3, we'd have 2 of them, and they'd be this value 4 for these two endpoints. All right. Let's go to the next slide. I think I can do that. All right, so theorem 3.1, the extreme value theorem. It's kind of common sense, but if f is a continuous function, so let's review what continuous means. No jumps, no holes, no vertical asymptotes. It could have a sharp turn. It could have a vertical tangent. Also no oscillations. So a continuous function, no jumps, no oscillations, no holes. So if we have a function like that in the interval from a to b, including a and b, then f has both a max and a min on that interval. Love this writing with my mouse, huh? All right, because if you have a function and a closed interval, like from here to here, you've got to have a high point and a low point. Even if it's a straight line, There's got to be some point that's higher than another point or lower than another point. Even if it's horizontal, then both of these points, every y value here is the max and the min, okay? So if you've got a closed interval, you for sure have a maximum and a minimum. That seems kind of logical, right? That we're always going to have a max or a min. Well, what if we're talking about an open interval? Oh, I guess you don't want to see that. What about if we're talking about an open interval? Will we always have a max or a min? These are called relative extrema when we're talking about an open interval, okay? The relative extrema, not absolute extrema, but relative extrema, are the maximum or minimum values of the function on an open interval. So that means we're not including the endpoints. So if you look at this graph from 5 to 8, here's 5, and here's 8. So we're not including the x values of 5 and 8, so we can't include the y values. What's the min? Okay, you can see that there's a minimum point right here. But what would be the maximum? On this interval, there is no highest point, because as we get closer and closer to this, it would be the highest point, but we can't include those points. So we can't include that endpoint, so we don't have a highest point. So there is no, or the minimum is this value here, 263, whatever that matches with this y value here. But the maximum between 5 and 8 would not exist. What about between 3 and 5? Would there be a maximum? Here's 3, and here's 5. Yep, there's a maximum right here at about 450. But between 5 and 8, there's no max. What about a minimum between 3 and 5? Reveal that there. Okay, 452. Between 3 and 5, is there a minimum? No, there's not. There's no lowest value because the endpoints, which aren't included, would have been the lowest points. We'll go back to that if we need to. So sometimes there is no min and sometimes there is no max. These are closed endpoints. There's the max, but there is no minimum value because that point is not included in this graph. If we have this graph with open endpoints, we have no maximum, but we do have a minimum. This graph, closed endpoints, and its continuous function, there is a minimum and there is a maximum. This graph with vertical and horizontal asymptotes has no min and no max. So you may or may not have a min and a max, but going back to theorem 3.1, if it's a closed interval and it's continuous, so no holes in the middle of it, we know it's going to have for sure a max and a min. All right, so how do we, or where do maxima and minima occur on a graph? The only possibilities are when the graph has a horizontal tangent line, or at a cusp, remember that's a sharp turn, or a jump, because that could be a highest or lowest point, or at the endpoints for absolute extrema. So how do we know algebraically if there is a horizontal tangent or a cusp or a jump? Well, we've got to find where the derivative, remember the derivative stands for slope, so we're finding where the slope of the tangent line equals 0. What is that going to mean? It's going to give us a horizontal tangent. We've done a few problems like that where we've found the question has been, where does this graph have a horizontal tangent? The purpose of that is leading into this. We want to know where a graph has a horizontal tangent because that means it's going to have a max, there's a horizontal tangent there, or a min, that would be a horizontal tangent there. So if we take the derivative and set that equal to 0, that will give us a horizontal tangent, so that will be a max or a min. Another place where a graph will have a max or a min is where the derivative is undefined. So remember that means where the derivative would have, like you'd end up with a 5 over a 0 or something like that. Or where there's a sharp turn, so there is no derivative. Or where there's an asymptote or a vertical tangent. This would be the vertical tangent example here. Or if there's a jump or a vertical asymptote, those are also places where the derivative is undefined. So that means where it's not differentiable. Sharp turns, holes, oscillations, all those crazy things that go on with graphs are all places where the graph is not differentiable. So then it would have a possibility of having a max or a min. So we have to think about those points as all the possibilities. We're looking for possibilities of where a graph could have a max or a min. And then we're going to test them to see if they are maxes or mins. So the places where relative extrema could possibly occur are called critical numbers. Critical numbers occur where the first derivative equals 0 or where the first derivative is undefined, like at cusps, jumps, holes, or vertical tangents, or vertical asymptotes. I guess I forgot to write that in there, or vertical asymptotes. All right. So the definition of a critical number, let f be defined at C. So for sure we're talking about a critical number where the original function is defined, so it's continuous there. If the derivative at that point equals 0, or if f's not differentiable at C, then C is a critical number. So C has to be a place on the original graph that is a place, not like a vertical not a vertical asymptote, not a hole, okay? Then C could be a critical number if the derivative equals 0 or if the function is not differentiable, so if the derivative is undefined. Those are two possibilities, the only possibilities, where a graph could have a possible max or a min, except at endpoints if we're talking about closed intervals. Theorem 3.2, relative extrema occur only at critical numbers. So we're talking about relative extrema, not endpoints of graphs that have the closed interval. If f has a relative a relative maximum or a relative minimum at x equals c, then c is a critical number. Kind of a basic theorem, nothing really to memorize there, just kind of know the concept. To find relative extrema on a closed interval, this is important, we're going to do this a lot. To find a relative extrema on a closed interval, so we're talking about a closed interval, find critical numbers, call them c. Find the y value at each c. So when we find critical numbers, that means we're taking the derivative and setting it equal to 0, and then taking that derivative again and finding out where it's undefined. We're going to call all those x values c. Then you plug them into the original function to find the y value. Then find the y value at each endpoint. So we're looking for absolute extrema too. And then compare all those y values and choose the highest or lowest. Well, choose the highest for the max and the lowest for the min. All right, so critical numbers. Take the derivative, set it equal to 0. Take the derivative, if it's got a denominator, set that equal to 0. Find the y value at each of those critical numbers you just found. Find the y value at the endpoints. And you're going to forget that later, because later we're going to be doing open intervals, but I want you to always go back to this lesson and remember to check the endpoints. Please check the endpoints for closed intervals. That'll always get you. All right, and then we're going to compare y values. So 2x minus 3x to the 2/3, find the critical numbers on the interval from -1 to 3, including -1 and 3. I showed you the graph there, but we're going to pretend we don't have it, okay? So we take the derivative. Sorry again about the writing. The derivative of 2x is 2, and then the derivative of 3x to the 2/3, you take the 2/3 out in front and multiply it times the 3. Subtract 1 from the exponent, so it's going to be -1/3. So we want to set that equal to 0. Let's just simplify it a little bit here. The 3's can cancel, and the x to the 1/3 goes in the bottom. So it's easiest to set things equal to 0 if they have a one common denominator. So let's multiply this first, 2 by 2x to the 1/3 on the top and the bottom, and then combine them as one big fraction. So if we want to set that equal to 0, when a fraction equals 0, only the top needs to equal 0. So we'll have 2x to the 1/3 minus 2 equals 0. I'm going to need to start another video here in a second. We add 2 to both sides, divide by 2, so we'll end up with x to the 1/3 equals 1. Cube both sides, so third power on both sides, so x equals 1. So that's one of our critical numbers, and you can see right here at x equals 1, that is a place where we have a horizontal tangent. So that's a critical number. I'm going to stop this and then you can watch the next video for the end of it.